Imagine that this is our door, and we are looking as if we're on the roof looking downwards towards the door. So our door handle is something like this. Okay, so does that give you an idea? The little triangle I'm putting here is considered the pivot point, also called the fulcrum. There's a variety of other names that can be used to describe this point, but in general, I will use pivot point, or fulcrum to describe the point about which it rotates. That would suggest that through that point lives the axis of rotation. So, as I'm labeling these, I'll remind you that we have the right-hand rule in discussing the direction of rotation, and it involves the axis of rotation. So understanding where your pivot point is and your fulcrum is, and understanding the way in which your system can rotate, that establishes how the right-hand rule is going to work. Yesterday we talked about the fact that to apply a torque means to apply a force, and the application of that force is one part in determining the size of a torque. So when we talked about torque, we're going to use a lowercase tau for the symbol for torque, and we know that it's related to two factors, the size of the applied force and where the force is applied. And today we're going to be more specific. We're going to use R to represent where the torque is applied. And to kind of establish that, R is a measurement of the distance from the fulcrum to the point where the force is applied. So this will represent our value for R. And we call this the torque arm length. So this is where we apply that force. And obviously for the door, we could apply it anywhere we wish on the door. But when we decide on a location, the next thing we'll have is the actual force itself. Now, how hard you push on the door, or how hard you pull on the door. So when we talk about applying a torque, it's a combination of two factors: the torque arm, which is where you apply that force, and the size of that force. There's one more factor involved, but I want to see if you guys can kind of work out how this would play out. We know that these two things contribute to the size of our torque, and they do. They contribute directly. It's a multiplication. So you double the length of the torque arm, you're doubling the size of the torque. You double the size of that force, you're doubling the size of the torque. But also there's how you apply that force, the effectiveness of it. And that's a little bit more complicated. Not much, but I want you to consider, I've drawn this indicating that we're applying that force perpendicular to the door. Would we be effective if we applied the force on the door this way? Like grab the handle and pulled towards the hasp? Would that be an effective way of opening the door? And obviously, I could consider the reverse of that. Would it be effective to say push on the door here to get the door to open? Is it clear that the angle that we choose to use determines how effective that force can be? So there's going to be a trig function involved here. And depending on how we decide to measure our angle will determine which trig function we're going to use. And the way the angle is measured is the angle between the torque arm and the direction of the applied force. This angle or this angle. Either one of them will work because of the way trig functions work. So it doesn't matter which one of these you choose to use. And we're going to label them both with the Greek letter phi. That's the angle we're going to use. The reason this angle is chosen, as opposed to other alternatives, like you could have chosen the angle that is, relative to the normal to the door, but we don't. We don't use that angle. We use this angle for a couple of reasons. One of them is it's related to the way the sine function works. The sine function reaches a maximum at 90 degrees and a minimum at 0 and 180, which is what we want. We know that we will get the most effective force if we take this force and apply it perpendicular to the door. This is going to be most effective. Any angle that we don't, that is off axis, is going to be less effective at opening the door. The sine plays that out because the sine is giving us a maximum at 90 degrees, and any other direction is going to be less effective, with 0 and 180 being completely ineffective. So when we write out our torque, the size of the torque is written like this. It's the size of the torque arm, size of the force, and the angle upon which you apply it. Now, unfortunately, torque is a vector. Just like any of the rotational values that we've had in the past, there's a direction to torque. And consider the door. There's you attempting to open it, and then there was, yesterday, Sam slamming it in my face. So if you guys know who Sam is, Samantha, she's in second period. She slammed the door loudly yesterday, right in my face. So when you see Sam, you should say that I'm very angry about it. You should know that I brought this up in every class that she's not in. And I brought it up in her class yesterday. And I even brought it up when she was trying to defend her AP capstone project. So if you have an opportunity to talk with Sam, say that I'm still really upset about her slamming the door. But she applied a torque that assisted the evil box in closing the door. That's a torque that we know is in this direction, upwards through the hinge. You guys remember our right-hand rule? Now, torque has direction because if you want to open the door, you want to apply a torque that is downwards through the hinge. So torque is a vector quantity. And because of that, we truly have to write this in terms of its vector properties. So there's a way of writing this, and you've not seen this before. So for those of you who have never looked at vector multiplication before, we've already done one version of vector multiplication. We did the dot product, and that was with work. So as a brief aside, if you remember, if you're trying to do work on an object, so we're going to try and take a box and we're going to try and move it from one place to another, and we might do so by applying a force. The work done was equal to the force dot the displacement. But work was a scalar. It determined how much energy was delivered to the box. And energy doesn't have a vector property. So this product was supposed to be about figuring out how much of the force was in the direction of motion, because only that portion of the force was doing work. So we used the cosine in this case, but the dot product took two vectors and created a scalar by telling us how much of the force was in the direction of motion. Torque is different. We're talking about how much of the force is effective at causing a torque, and we have most effectiveness at 90 degrees. But we also need to be left with a vector. So we write this as something called the cross product. You see, the torque arm is a vector. It points from the axis of rotation to the place where the force is applied. So R is a vector value. And of course, we already know that force is a vector value. These two vectors are used to determine the size and the direction of the torque. So this relationship represents the magnitude, the size portion, how big the torque is. But the cross product is a reference to how we figure out the direction of the torque. And the direction of the torque is based on the right-hand rule again. And so the cross product is written in a particular order to help us use it to determine the direction. So about, say, kinematics, we dealt with only one-dimensional motion, if you'll recall. So most everything we did was either a positive direction or a negative direction. That's going to be true for most of what we do with rotational motion. Most things are going to rotate clockwise or counterclockwise. So we're going to have less worry. Oh, you gotta be kidding me. need this bright light behind me? Do you like that? Being backlit? It's bothering me. So anyways, for most of the rotation stuff, it's going to be still one-dimensional. Things are going to rotate clockwise or counterclockwise. But you're required to know the right-hand rule. So there'll be some opportunities to use it, but it's still only going to determine, is the door going to open or is the door going to close? Is something going to rotate clockwise or is something going to rotate counterclockwise? We're going to practice here. For practice, we're going to do a statics problem. And we've done statics problems before, but I didn't call them a statics problem. So a statics problem is a Newton's first law problem. A Newton's first law problem says that the net force equals 0. But now we know things about torque. So statics involves not just force, but is also going to involve torque. Statics occurs when both the sum of all the forces and the sum of all the torques equals 0. Okay, that's what a statics problem is about. So we're going to do a statics problem here to practice torque. You guys are going to do an activity like this in just about a day. We're going to do it tomorrow. I have a loop of string and just a meter stick. I suspect the meter stick has a center that's somewhere around 50, but they're not perfect. So I kind of want to figure out where the center is. This is going to be important for what we're going to do next. So when I find the center, you should write it down. It's not quite 50. All right, so it is 49.8 seems to be the center of the meter stick, maybe 49.7. But that's pretty close. The center of the meter stick is 49.7 centimeters. I don't know the mass of the meter stick. That's important because we need to know its center, but I don't know its mass. We're going to try and figure out its mass because what I have up here somewhere, I left it, here you go, is a 100-gram mass. Okay, so this is 100 grams. What I'm going to do is I'm going to put the meter stick so that it's off center. There's a torque acting on the meter stick right now. That torque is the center of mass of the meter stick, which we found to be at 49.7 centimeters. I'm bringing that up because it's causing a downward force on the meter stick, but I have a pivot point placed wherever this loop is. Does everybody understand? The pivot point is acting as our fulcrum. I'm going to put the pivot point someplace convenient. So I'm going to say, I'll put it 35. That's convenient enough. So it's not, I could put it at 40, I guess, but I think it'll work best if I put it a little bit further away from the center. Now, I'm going to take this paper clip, which has very little mass compared to the weight, and use it as a way of hooking my weight to the meter stick. What I'm going to try and do is bring the system into balance. Closer. That's on you. Closer. There we go. All right. I'll say that I'd say our system is in balance. You guys agree? Unfortunately, while I was messing with it, I shifted where the fulcrum is. But I think it's clear that the system is in balance. That means there's two torques acting on the meter stick. There's the torque that I added, and then there's the torque from the weight of the meter stick. Both acting on the meter stick. I want to use it to figure out what the mass of the meter stick is. Unfortunately, the fulcrum shifted, and it is at 36.2 centimeters. And my mass is hung exactly at 25 centimeters. So we're going to draw this real quick. I have a downward force of 0.1 kilograms times 10 meters per second squared. This is the downward force that I'm applying. There's a fulcrum or pivot point that's somewhere around 36. In fact, it's at 36.2 centimeters, while my downward force is at 25 centimeters. The meter stick has its own weight. I don't know what it is, but we know that it's at 49.7 centimeters. And it's applying a force of unknown value. We'll say the weight of the meter stick. There are two torques acting in our system, creating the conditions for the net torque to be equal to 0. Now, there's actually 3 forces acting on the system. Can you name the force I'm leaving out? What's that? Tension. The string is applying a force. But I left it out from our conversation of torque. But there is an upward force acting. That's tension. The reason I left it out, and this is worth writing down, is tension acts at the fulcrum. Because it acts at the fulcrum, the torque arm length is 0. So any force that acts at the fulcrum can't apply a torque. Any force that acts at the fulcrum can't apply a torque. All right. Here's what I'd like to do. I'd like to figure out the size of the mass of the meter stick. I know that there are 2 torques acting in our system. There's the torque from the mass that I applied, and there's the torque from the weight of the meter stick. All right? We know they have to add up to be equal to 0 because we're in balance. If the system was unbalanced, it wouldn't work, but the system is all balanced, so we're good to go. Torque is going to be torque arm length, force, and then something about the angle. So let's start with figuring out what we know about this. We're going to need all 3 pieces for each of our forces. So start with the mass. The mass is located at 25 centimeters. First thing I need you guys to do is figure out what the length of this torque arm is. What is the torque arm length for the mass that we applied? It's just subtraction. You guys can do it. I believe in you. What's that? Yeah, it's just 11.2 centimeters. Yeah, it's from 36.2 to 25. So I probably, if I was doing this right, would convert this into meters. So let's convert this into meters. If it's 11.2 centimeters, that means it's going to be 0.112 meters. All right. What's the size of the force that we're applying to the meter stick? How'd you get that?
0.1 kilograms times 10 meters per second.
Yeah, that's it. So 1 Newton. All right. Can somebody make a guess as to what the angle is? Yeah, it looks like 90. The meter stick looks like it's horizontal, doesn't it? And the force is straight down, so I think 90 degrees will be okay. So I'm going to put sine of 90. All right. I did one of them. Let's do the next one. How far is it from our fulcrum to where the center of mass of the meter stick is?
0.135.
I'm sorry, go ahead.
0.135.
Okay. I assume you subtracted 49.7 from 36.2. Now, we don't know the weight of the meter stick. We know that it's going to be a product of the mass and gravity, but we don't know the weight of the meter stick. So I'm going to put just that, m times 10. Is it reasonable to conclude that the sine of 90 is going to be applied here as well? That the force is downwards and the meter stick is horizontal? All right. Torque is a vector quantity. So we have to deal with the fact that one of these torques is in one direction and one of these torques is in the other. So our pivot point is in the middle. So when I try to work this out, I'm going to use the right-hand rule to figure out the direction of each torque. So R is this way for the mass that's being applied, and the force is downwards. That's a torque that is out of the board and is causing the meter stick to rotate this direction. Now, like any one-dimensional problem, we will have to decide if out of the board is positive or out of the board is negative. You get to decide. So do you want out of the board to be positive, or do you want out of the board to be negative? Just gotta pick one. What do you got? All right, so out of the board is negative. That means this torque is negative, because that's the one that's out of the board. By the way, to add to this complexity, we now have kind of a three-dimensional thing we have to deal with, because we're talking about out of the board and into the board. There is a symbology that goes with out of the board and into the board. And the symbology for a vector that is out of the board is a circle with a dot inside. This is out of the board. And a symbol for into the board is a circle with an X inside. That's into the board. AP will use this symbology on the exam. So this is supposed to be an arrow, because we use arrows to represent vectors. So imagine if an arrow is pointed at you, you would see the point, and thus a circle with a point in it. And if the arrow was faced away from you, you would see the fletching of the arrow, the feathers. And that's why you see the X. So that's where the symbology comes from. But we're going to use out of the board, and into the board we'll use a dot for out of the board and a cross for into the board. Our other torque, right-hand rule, torque arm from the pivot point to the force is this direction. The force is downwards, so our thumb points into the board. So if out of the board is negative, into the board is positive. That makes our other torque positive. All right, that's it. You can figure out the mass of the meter stick, can't you? Do you see what you're going to have to do here? Take a minute, work it out. I don't want to do the arithmetic. That seems like a you job. 0.083. Zane, do you agree? I do. All right. Is there anybody who needs me to work that out? This seemed pretty straightforward, but okay. I'm going to take and look at their two vectors. The first vector, 1 times 0.112, is going to be negative 1.112 meters times newtons. Our next vector, plus 10 times 0.135, so 1.35 m, has to sum to be equal to 0. Now, this mn is just the units, so let's ignore it for a minute. And I'll get negative 1.112 equals 1.35 m. So m is going to be, I'm sorry, this will be negative because I moved it over to the other side. So negative 1.112 divided by negative 1.35. Does that make sense? Any questions about that? Is that good, guys? All right. Units are meter, Newton, but the bottom one is kind of weird units because we took meters and multiplied by 10, which is meters per second squared. But that's going to leave us with just kilograms when we work that out. So whatever we got there, that mass, what'd you say, 0.8 what? That? No. Oh, thanks. Clearly indicating I don't listen to you guys, but I should do better. This is a straightforward statics question. There's not a whole lot to it, but we're going to do some that are of a little bit more difficult quality, but we're just getting started. This is our first time calculating a torque, so there are a couple of things I want to point out here. So first, going back to our torque, it's a torque arm times a force. And when we want to get the magnitude, we have to bring in the angle. The angle doesn't have units, but the length of the torque arm does and the size of the force does. The units are meters times newtons. Now, I want to be really clear about this. When we calculated work, which was force times displacement, times the cosine of the angle, our units for this were newtons times meters. And we called this a joule as a unit of energy. This has no other name. We call it a meter newton, and the order tells us that we're talking about torque. So it's important that you understand meter newton is the unit for torque and is not a joule. Newton meter is the unit of energy, and it is a joule. So this is the first time where the order of the units makes a difference, but you need to be clear. Meter newton is a measurement for torque. It's how hard you twist or turn something. If you are working on anything in the United States, when it comes to a car, it's a foot-pound. So you guys who work on cars, foot-pound is the unit of torque that you work for almost all the bolts on your American-made car. But meter newton, that's the unit of torque for anything else made anywhere else in the world. So there are 4 forces acting on the bridge. The bridge in this case is that white plank. But there are 4 forces that act on the white plank. There's your weight acting downwards. There's the weight of the plank acting downwards. But there's the 2 supports acting upwards. The net force on the bridge is hopefully going to be 0, because if it's not, the bridge is going to accelerate, and you don't want the bridge to accelerate. But is it clear that if you're standing closer to one side, this support is going to support more of your weight than this support is going to? That as you walk across, that's going to shift from one support to the other. Tomorrow, we're going to have to figure this portion out. How do we deal with a problem like this?